The average rate of change between 2 points is given by the following formula. First, let's notice that these 2 points are the same thing as x1, y1 and x2, y2, but the y coordinates have been written using functional notation. So recall that the average rate of change between 2 points is the same thing as the slope of the line that contains those 2 points, which is y2 minus y1 over x2 minus x1, but our average rate of change formula is going to use the functional notation for y2 and the functional notation for y1. When we're looking at data in a table, we'll say that that data can be represented by a linear function if the average rate of change between each of the ordered pairs is a constant value. Stated slightly differently, we can say that if the average rate of change between any 2 points on the function is the same number, no matter which 2 ordered pairs we're looking at, if we get the same average rate of change all the way down the table, then we say that the data in the table is linear, and that the average rate of change that we get throughout the table is the slope of the line that contains all of the points. So let's look at an example. In order to determine if the data in the table is linear, we'll need to calculate the average rate of change between each pair of data points. And if we get the same number all the way down for every pair of points, then we'll say that this data can be represented with a linear function. So we'll start with these first 2 ordered pairs. The average rate of change is calculated by looking at the second y coordinate, which in this case is 14, minus the first y coordinate, which is 23, and we'll divide that by the second x coordinate, negative 2, minus the first x coordinate, which is negative 5. 14 minus 23 is negative 9, and negative 2 minus negative 5 is the same thing as negative 2 plus 5, or positive 3. So we get negative 3 as the average rate of change between these first 2 points. So now we'll calculate the average rate of change between the next 2 points. We'll say y2, which is 8, minus y1, which is 14, and divide that by x2, which is 0, minus x1, which is negative 2, so we're subtracting negative 2. 8 minus 14 is negative 6, and 0 minus negative 2 is positive 2, so again, we get negative 3 here. And so far, we have the same average rate of change, but we need to check all the ordered pairs all the way down. So we'll look at the average rate of change between the next 2 points, which is y2, negative 1, minus y1, which is positive 8, divided by x2, which is 3, minus x1, which is 0. So now we have negative 9 over positive 3, which is again negative 3. Now to calculate the average rate of change between the last 2 points, we have y2, which is negative 16, minus y1, which is negative 1, and we'll divide that by 8 minus 3, which is x2 minus x1. Negative 16 plus 1 is going to be negative 15 in the top, and 8 minus 3 is 5 in the bottom, which again simplifies down to being negative 3. So we did get the same average rate of change all the way down. So we'll say 3 dots in a triangle means therefore the data in the table is considered to be linear, which means there is a line that contains all of these ordered pairs. Now our directions say if the data is linear, we are to find the linear function that fits the data. And since the average rate of change all the way down was negative 3, that is also going to be the slope of our line, so we already know the slope. But in order to write the equation of the line, we need not only the slope, but also a point. Any point will do, but the y-intercept, if we have that, is definitely going to be the easiest. So let's choose that y-intercept as our point that we're going to use. Now there are a couple of ways that we can write the equation of the line, but since we have the slope and the y-intercept, I think it's easiest if we just go to the slope-intercept form. We'll use functional notation here because we are asked to find a linear function. And as a reminder, the equation of a line in slope-intercept form is f at x is equal to mx plus b, where m is the slope and b is the y-intercept. And since we have both of those values, we can just say the slope is negative 3, which is then to be multiplied by x, and the y-intercept was 8. So this is the equation of the linear function that contains all of these data points. Let's do this again for part B. We're asked to determine whether or not the data is linear, so we need to calculate the average rate of change between each of the pairs of ordered pairs. So we'll begin with the top two. We'll say y2 is -1 minus y1, which is -3, and then divide that by x2, which is -2, minus x1, which is -6. So we're subtracting -6 here. We have in the numerator -1 plus 3, which is going to be +2, and in the denominator we have -2 plus 6, which is going to be +4. So this simplifies down to being 1/2. And now we need to compare that with the average rate of change between the next 2 points. So again, we'll calculate by starting with y2, which is +1, minus y1, which is -1. Divide that by x2, which is 0, minus x1, which is -2. In the numerator we have 1 minus -1, which is going to be 1 plus 1, or 2. And in the denominator, we have 0 minus -2, which is going to be +2. And right away, we can see that we have a different average rate of change. So that means that we don't have to go any farther with our check. As soon as we come up with two average rate of changes that are different, we can tell that the data is nonlinear. So we don't have to search for a linear function because the data in the table is not linear.